So for those who are from outside the department, particularly warm welcome to you all. We really don't bite around here. And as ever, or I should say as ever, all the time around, and I hope forever, I'd like to particularly welcome Joyce Wheeler, who's been able to make it again. And as ever, you're very, very welcome, and sort of lounge in it all and enjoy it and tell us, well, tell Butler where he's getting it wrong. That would be rather good. And also, I might mention that Lois Lampson, Butler's wife, has joined us here today. So you're also, of course, very, very welcome. So our speaker is one of the most distinguished computer scientists and computer engineers in the world. Butler is a technical fellow at Microsoft Corporation and has been in that role for quite some time. But as you would have seen from his CV, he has worked in some of the world's most important research universities and research labs, industrial research labs in particular, over the years. So he's a technical fellow at Microsoft now and an adjunct professor of computer science and electrical engineering at MIT. I'll just pick out a couple of things from his CV. He's a member of the National Academy of Sciences and also the National Academy of Engineering. And the thing I'd like to pick out is his Turing Award in 1992, which was not quite before some of you were born, but getting that way, so it was a little while ago. And so may I just read the citation, which was at that point, and he didn't finish then. So, you know, this is like what they said. As part of the Turing citation in 1992, or as the Turing citation about Butler already at that time. So his Turing Award was for contributions to the development of distributed personal computing environments and the technology of their implementation. Workstations, networks, operating systems, programming systems, displays, security, and document publishing. In other words, everything. So that was many, many years ago, but well, no doubt he'll cover some of that and much more recent stuff as well. So if I could invite Butler to give the fourth Wheeler Distinguished Lecture entitled Hints and Principles for Computer System Design.
Thank you, Andy. It's a pleasure and an honor to be here giving the Wheeler Lecture. I never had a chance to work closely with David Wheeler, but he did come on sabbatical to Berkeley in, I think, 1966 or 67. And at that time, I was one of the designers of a time-sharing system that we were building for the one of the university's mainframe computers. And David entertained himself during his sabbatical by building the terminal controller to plug into this machine. And as is always the case with Wheeler's work, it was a masterpiece of economy and elegance. And fortunately, after he went back to Cambridge, it kept working because I'm not sure that anyone understood all the beautiful things that he had done well enough to fix it if anything serious had gone wrong. So that was an interesting experience. Much later, I had as a colleague Mike Burrows, who, together with David Wheeler, devised the famous Burrows-Wheeler compression algorithm, which has very similar properties. So on that note, 32 years ago, that's 2 to the 5th, I wrote a paper called Hints for Computer System Design. And for about 10 or 15 years after I wrote that paper, I would reread it every 2 or 3 years, and I never felt any strong inclination to revise it. But a lot of things have happened since then, and it now seems to me that there's a lot more to say about it. A lot more hints to give for computer system design than there were in 1983. I've been trying to write a new version of this paper quite unsuccessfully. And my problem is that I know too much now. At that time, I knew just about the right amount so that if you distilled it all down into slightly cryptic hints, you could fit it into one reasonable size paper. That's no longer true. So in this talk, I'm just going to skim over the surface. Please bear in mind these are hints. They're often not consistent. They're not precise. They're only suggestions. If you don't like one of them, just skip over it and go on to the next one. You're not allowed to pick nits because that's not appropriate for hints. There are a few principles that will come up in the discussion, and you can pick nits about those if you want to. So the whole talk is summarized in this little pair of acronyms, STEADY by AID. So there are a number of different ways that one can look at the problem of designing computer systems. Two of them are that you should think about what your goals are, and that you should think about what your methods are. So I've summarized most of the goals that you might have under this heading of STEADY. You might want things to be simple, timely, efficient, adaptable, dependable, and yummy. Yummy is represented by Apple, not unfortunately by Microsoft. And I've summarized about 3/4 of what I know about methods for designing computer systems under the heading of AID, which stands for approximate, incremental, and divide and conquer. And we'll hear a lot more about both of these things as I go along. So here's a summary of the goals. It's important to bear in mind that, of course, you can't fully achieve all of these things in any system that you design. The most important motivation for writing them down like this and reflecting on them is to think about which of these things are most important to you. Simplicity is a little bit distinctive because almost always it's better for your system to be simpler rather than more complicated. But for the others, depending on what kind of system you're building, you may make very different judgments about what's important. If you're starting a company to do some flashy new web service like Instagram, and your goal is to sell it to Facebook, then timeliness is extremely important. Adaptability, not so much because you're going to sell out. Dependability, not really very much at all. If you lose some of the stuff, it won't really matter. And if you're Snapchat, it's even better because you're expected to lose it. So on the other hand, if you're building avionics software, then dependability is the most important thing. Yumminess is not important at all. The FAA is not going to be impressed. Adaptability plays some role. Efficiency is probably pretty important because you have to be able, the computers that you have to run on are probably somewhat limited in their capacity, and so on and so forth. So clearly from this list, you're not going to get any absolute answers. But you should be thinking about which of these things are most critical to you and put the emphasis there. And I've found a way to describe them all with words that begin with F, which might be another useful mnemonic. How to go about it. So that was goals. Now methods. Methods are, for most of us, really more interesting than goals, just because we like to hack. And I've classified those, as I said, under 3 headings: approximate, do things incrementally, and divide and conquer. Of course, divide and conquer is the most important, and I worked very hard to find an acronym that would begin with D. And I even considered adding some more words, but I couldn't find a good one. So we'll talk a lot more about these as we go along. Before I plunge into the how and the what, though, I just wanted to talk about a few overarching things that you should be thinking about when you're designing a computer system. Perhaps the most important one is to understand the difference between precise and approximate software. Precise software is software that has a spec, whether or not the spec is properly written down. And if the software doesn't satisfy the spec, the customer is going to be unhappy. So avionics software is precise, banking software is precise, Microsoft Word and Excel are precise. Customers have very little tolerance for messing up in any of those pieces of software. For approximate software, on the other hand, typically there isn't a spec, and even if there is, it's not very important. There's no spec for the results of Google searches. They're just doing the best they can. They have machine learning algorithms for ranking things, and they try to search the whole internet, but it's all kind of fuzzy. There's no spec for Facebook, really. There's not even a spec, it turns out, for the service that a company like Amazon offers on its retail website. For these kinds of things, what's important typically is agility, getting it out there soon and being able to change it quickly, and making it cool so people will really like it. It's not that one kind of software is better or worse than another. The tradition in computing is to think, of course, precise software is better. In fact, that's the only kind that's sort of real and serious. But that's not actually true. 30 years ago, there was very little approximate software in the world, but now I think at least half of the software that's written is approximate. So the important thing is not that one kind is better or worse than the other. The important thing is that you need to know what kind you're writing. Because if you are writing precise software and you think it's approximate, then it's not going to satisfy the spec, and the customer is going to be very angry. And if you're writing approximate software and you think it's precise, then you're going to invest an enormous amount of engineering effort in figuring out what the spec is and writing software that satisfies it. And the customer is not going to value that, and your software is going to be late, and it's not going to be cool, and that's going to be a disaster of a different kind. So it's very important to get your head straight about this. A second theme, overarching theme that I wanted to touch on is the notion of what I've called coordinate systems. In many cases, you make your life much easier by choosing the right coordinate system. If you remember your high school physics, you remember that many dynamics problems are much easier to solve in the center of mass coordinate system. Many things about matrices are much easier to understand if you rotate the coordinate axes so that they run along the eigenvectors. And the two examples of this that I want to, there are many examples of this, but the two that I want to touch on in a little bit of detail are thinking of state as being versus becoming, and thinking of functions as code versus tables versus overlays. And I'll talk a little bit more about both of those. The other thing that's related to choosing a good coordinate system is choosing a good notation. And that has several aspects. One of them is the vocabulary that you use. You want to have types and methods that are well matched to your problem domain. You want to have syntax that makes it comfortable and reliable to express the things that are important to your particular problem. And you want to have powerful primitives. And my experience has been that the best primitive to make friends with is relations, because a lot of other things that you typically run across are special cases of relations. Functions, graphs, tables, state transitions, those can all be thought of as relations. And there's a way of thinking about how things work with relations and transitive closures and the graph structures that you can develop from relations and so forth that will take you a long way. So what about state? The standard way to think about the state is, okay, there are variables x, y, and z, and the state of a system that has variables x, y, and z is tell me the value of x, tell me the value of y, tell me the value of z. That's very straightforward. That's state as being. State as a map from names to values. The other way to look at the state, though, is in terms of the operations that got you there. So first, in this particular case, the operations are probably boring. I set x to 3, I set y to 17, I set z to 0. But in many cases, the operations are much more interesting and complex. So the being is the usual form, but the becoming form is good if you want to undo, because you want to take away some of those operations. It's good if you want to have multiple versions and represent them compactly and explain the relationships between them to the client. And it's good for recovery. So some examples of this contrast: if you have an image that you're planning to display on a screen, the being way of thinking about it is the bitmap, the values of the colors at every pixel. The becoming way of thinking about it is the procedures that you executed to make the image. I drew a line here, and I put down a rectangle here, and I pulled in this picture, this piece of clip art from somewhere else, and so forth. And For a document, the being form is just the sequence of characters that make up the document, decorated, of course, with fonts and other stuff. And the becoming form is the sequence of insert and delete operations that I executed in order to get there. For a database, the being form is the table in the buffer cache, and the becoming form is the redo and undo log, and so on and so forth. And I think you can see from some of these examples that the becoming form is good for the purposes that I suggested. I first got familiar with this notion when I spent a lot of time trying to understand how recovery works in transaction systems, which is fundamentally based on the idea of redo logs, which is definitely it's a classic form of becoming, but it applies in many other contexts as well. Very often when you're trying to figure out how to structure your system, it's a good idea to ask yourself, should I tear my head away from the classic way of thinking about the state as the current values of the variables and think about it instead in terms of the operations that I executed to get there. For functions, this is a fairly different way of classifying things. Usually when we think as computer scientists about a function, we think about code that you can execute in order to produce some value, which is the value that the function returns from a particular set of arguments. And that's typically the way, well, I'm not sure how mathematicians think about functions, actually. Let me not go there. But in many cases, an alternate way of thinking about a function is that it's a table. And in fact, if you remember the way you learned about functions in undergraduate mathematics, they'll tell you that a function is a set of ordered pairs. And the computational view of the function comes a bit later. And then a third way that's often very important in computing is to think of a function as an overlay. You have a partial function, f1. You see if f1 is defined on the argument that you're interested in. If it is, that's the value. Otherwise, you go on and try f2 and maybe several of these. And I've given a bunch of examples here of how these different ways of thinking about functions materialize themselves in computer systems. And of course, typically there's more than one of these at play. Well, one of the canonical examples is so-called memoized functions, where you have code that you can execute to run the function, but it's fairly expensive. And it's valuable in many cases once you've executed the code, to save the result in case you're going to need the value of the function again. Okay, the final overarching theme that I want to touch on has to do with specifications. People who like formalism like specifications. Most people who build systems don't like specifications, and they think they're not worthwhile. And of course, when I was young and naive, I thought that too. But now that I'm old and wise, I know that there's a big payoff to writing a spec. If you do it in the right way, typically the way people go astray is they put too much formalism into the spec and too much detail. And they lose sight of what the different benefits are that you can gain from writing specification. So I would say for any kind of system you want to build, it is always worthwhile to write down what the abstract state is. It's usually not very big and complicated. And if you find it getting big and complicated, that's almost always because you put too much detail into it that shouldn't have been there at the highest level of abstraction. A lot of people think somehow that the bits and bytes in the memory and on the disk are real, and these abstract states are not real. They're imaginary things that you conjured up, and so they can't be that important. But if you think just for a moment, you'll realize that this is a ridiculous point of view. From the point of view of the device physicist, the bits and bytes have no reality at all. Right? What's really going on is that some electrons caught on a little bit of silicon, and there's magnetic domains on spinning platters. And all this stuff about bits and bytes is completely imaginary, things that were fantasized by the computer scientist. So if you believe in bits and bytes, then you have to believe in abstract state. So canonical simple example, what is the state of a file system? Well, it's a map from path names to byte arrays. That's what it is. It's really not that complex. It wasn't that much work to write it. It was a fair amount of work to figure out that that's the right way to think about it, but it's not very much work to write it down. And even when you decorate it with a few other details about permissions and stuff, it's still not very complex. This always pays, writing down the abstract state, in my experience. And most people have a great deal of difficulty in doing it. The next thing you should do, if you maybe writing down the abstract state is all that's worthwhile for your project, but very often it's a good idea to take the next step, which is to write down what the interface actions, which today are called APIs for reasons that are not entirely clear to me. These are the operations that you can do on the state. Understand which ones are external, which ones are taken internal by the system without any, for example, garbage collection things are internal actions. So here's a very simple example. If you want to understand how a system behaves in the presence of failures, typically the way to think about it is that there are actually two pieces of state which are called the volatile state and the persistent state. And when there's a crash, the volatile state gets reset from the persistent state. And when you do a sync operation in the file system, for example, you set the persistent state to be equal to the volatile state. So again, it was a fair amount of work to understand that this is the right way to think about it, but it's actually not very hard to write it down. Okay, now things get a little more problematic. Whether it's worthwhile, my view is that it is always worthwhile to write down the state, and it's almost always worthwhile to write down what the interface operations are and what they do to the abstract state. And if you can't do that, it's a pretty good sign that you don't actually understand what you're doing. The next step is more speculative, and I wouldn't advocate that one should always do the next step, but it often pays off. And the idea of the next step is we have the abstract state. You also you're contemplating an implementation, so you're going to have a concrete representation in terms of bits and bytes or arrays and databases and whatever of the abstract state. And you'd like to know what's the connection between the implementation, between the code and the spec. And the way to establish that is to write down what's called an abstraction function, which is a function that, given the implementation state, will tell you what the corresponding abstract state is. And my experience has been that writing this down is quite a bit more work than the first two steps. At least it will require quite a bit more ink, for sure. And it may require quite a bit more thought, too, to figure out exactly how is it that your intended implementation is representing the abstract state, because that's the question that the abstraction function is answering. And then we get to the fourth step, which is if you actually want to do a correctness proof for your system, the way you do that is you know what all the actions are. That was point 2. You know what the abstraction function is. What you have to show is that, is this going to wiggle around? Yes, great. What you have to show is that for every step that the code takes in going from state S to state S prime, if you map that up to the spec using the abstraction function, the abstract action takes f of s into f of s prime. And the magical thing about this is that, number one, you can do this one action at a time. You never have to think about more than one action at a time. And number two, this always works. There are theorems that say that, subject to some curlicues that I'm not going to talk about, any system can be the correctness of any implementation can be demonstrated using this piece of machinery. So this always works. You do not have to learn any other ways of doing business. If you're interested in pursuing this further, I strongly recommend a recent paper by some people from Amazon, which they published in the Communications just a couple months ago, explaining how they've been using all this machinery to do real work on various components of Amazon Web Services and maybe the Amazon retail website too. This, by the way, is, in my experience, is extremely unpopular advice. Many people say these things to programmers and architects and system designers at Microsoft, and usually all of these suggestions are indignantly rejected as a waste of time. But my experience tells me that they're not a waste of time, and the Amazon guys confirm that coming from a very different place than I come from. Okay, so much for overarching thoughts. Now I want to talk in more detail about some of the methods that often work well in building a computer system. The most important one by far is divide and conquer. Why is it so important? It's important because we're not that smart and we can't keep that many things in our head at the same time. And the only way to make progress is to break things down into pieces that we can understand individually. This is not so important if the system is small enough that you can actually keep everything in your head. And if you have enough willpower, maybe you can just push it through. And I think David Wheeler must have been an interesting example of both of these things, because on the one hand, he could keep a lot of things in his head and push something through that was much more complicated than probably I could push through. But on the other hand, David Wheeler invented subroutines, which were the first form of divide and conquer, I think, that actually surfaced in computing. So the essential idea, well, I'm going to tell you about 4 flavors of divide and conquer. This one's the most important. And the idea is to divide things by their differences somehow. And the motivation for it is to limit the complexity of what you have to think about at any given time, and liberate the pieces that you divide your system into so that they can evolve independently. So the way you do this is by having abstractions and having interfaces to the abstractions. And the whole point of an interface is that it tells the client of the abstraction everything that they need to know in order to use the abstraction effectively. And it tells the implementer of the abstraction everything that they are responsible for doing in order to satisfy the clients. And in that way, the interface decouples the concerns of the client from the concerns of the implementer. And that is the most fundamental tool for building complicated systems. So I've given several, on all these slides, I've put some concrete examples of these things in this dull red. And I'll just touch on 1 or 2 of them. I don't have time to talk about all of them by a long shot. TCP/IP, of course, is one of the most conspicuous examples of a successful abstraction. Underneath the abstraction of IP, there's an immense variety of different ways of packaging the bits of an IP packet up into the bits of some lower level thing, encapsulating them often many times, and transmitting them over an immense variety of physical media, ranging from wires to fiber optics to radio there are many examples of systems in which IP packets are transmitted over another TCP/IP network, so you can nest the whole thing. And that might seem at first to be just an academic curiosity, but it's actually very widely used, and in the networking world goes by the name of overlay networks. And on the client side of the TCP/IP interface, we have an enormous variety of different applications that depend on it. Email, Twitter, the web, file transfers, voice calls over the internet. Again, an immense range of different things that run on top of that interface. So this is probably the single most dramatic example that we have in the whole world of computing of an abstraction that has enabled an amazing variety of independent evolution on the 2 sides of it. Probably the next best example of such a thing is the file system, where again there's a fairly simple interface. You go from as I said earlier, you go from path names to arrays of bytes, and then you all know hundreds of applications that make use of files, and probably those of you that are into system design know dozens of different ways to implement that abstraction, using a variety of different storage devices and a variety of different data representations for things, and so on and so forth. Sometimes it's good to package up the abstractions a bunch of different abstractions into what's typically called a platform or a layer of software. And I used to think this was kind of a stupid idea. Why not just let each abstraction and each module stand on its own? But actually, it turns out to be very important when you think about how are you actually going to ship things. Because when you evolve from version n to version n+1 of something, that's often traumatic for the client. And you don't want them to have to think about it too often. So if I've gathered a whole bunch of abstractions together in the form of a platform, I can just evolve the platform from version n to version n+1, as opposed to communicating with the clients independently about each one of the dozens of modules that compose the platform. So the canonical examples of that are things like operating systems and databases. But there are many others. Another interesting angle on abstractions is people often say, and I think correctly, that it's good if your programming language is declarative. I committed myself to write a paper about this for Alan Kay's 70th birthday festschrift a few years ago without thinking about it too carefully. And when it came time to actually write the paper, I realized that I had no idea what declarative programming actually is. So I went to the internet and I poked around for several hours, and I came to the conclusion that nobody knows what declarative programming actually is. It's just that it's good. But after chewing on it for a few days, I came to the conclusion, I know what it is now. And the answer is, a program is declarative if it only takes a few steps. Now, of course, internally, it's going to take jillions of steps, because the computer executes 1 billion steps per second. But I should only have to think about a few steps. So that means, for example, that a declarative program cannot have a loop, because a loop takes lots of steps. And a declarative program cannot do imperative recursion either, because that also takes, that's just another way of dressing up a loop. Beyond that, well, you can look at the program that you're writing and ask how many steps. Then you'll know whether it's declarative or not. I think we'll skip over this synthesis thing. So that was dividing by difference. The essential idea is interfaces and abstractions. What about other ways of doing divide and conquer? Well, of course, you all know about recursion. Here the idea is to divide by structure somehow and make the part similar to the whole. So quicksort is a canonical example of this from the algorithms domain. In a very different space, distributed hash tables are an example of doing things recursively, where you organize a large number of flaky nodes into a ring, and you get from one place to another on the ring by moving first halfway across the ring, and then a quarter of the way across, and then an eighth of the way across, and so on and so forth. Path names for files and IPv6 addresses are an example of recursion in the space of naming, and file systems similarly. So recursion is good. Replication is the crucial tool for fault tolerance, where the idea is that you're dividing not in order to make your system more intelligible or in order to exploit its structure, but in order to make it more available. The essential idea behind redundancy is to divide your system into pieces, all of which are doing more or less the same thing if they work, and where you can tell one way or another whether they're working or not. And there's two ways to do that. You can do it in time, or you can do it in space. When you're doing communication, typically you do replication in time, and it's called retransmission. And the canonical example of that in today's networking world is TCP. When you're doing it in space, you're doing it typically in order to deal with the primary motivation for doing it is to deal with the possibility that one of the mechanisms might fail, and you want the overall system to still keep working. And the basic technology for that is something called replicated state machines, which is a systematic way of making it so that n copies of something will behave like a single, more reliable copy, in spite of the fact that there's concurrency and failures and other complicated stuff going on. And finally, you could divide things up concurrently, which typically you do for performance. Now that we no longer get for free from the device physicists a faster single stream execution every 2 years, the way we get more performance is to have more copies of the same computing engine that runs at the same speed. And that means you have to figure, if you want your program to run faster, you have to figure out how to break it up into pieces that can run in parallel. And my slogan for concurrency is this one: stripe, stream, or struggle. So what does that mean? The easy way to do concurrency is to break things up into pieces that don't need to communicate with each other at all, because they operate on disjoint parts of the state. And in the world of disks, that's called striping. It has many other names in other parts of computing. And if you know how, for example, how MapReduce or BitTorrent work, you know that they both depend on striping in order to take advantage of the lots of machines that are available. The idea of streaming is basically you line the different concurrent things up in a row like this, and the data flows through them. So the generalization of a pipeline like that is called data flow, and MapReduce also uses data flow to get more performance. If you can't figure out how to make your program run fast enough by either striping or streaming, then you're going to have to work hard. And that's best avoided. If you are going to do that, I have a tiny fragment of advice which I haven't put on the slide, which Greg Nelson explained to me many years ago. He said there's two kinds of concurrency. There's easy concurrency and hard concurrency. And by the way, striping and streaming are very easy concurrency. So they're definitely to be preferred. So the idea of easy concurrency is there's a very simple rule for making your program work, which is you have to lock a variable before you can touch it. And that will keep different parts of your program that are touching the variable at the same time from getting into trouble. Of course, this is grossly oversimplified. But if you're not going to follow that discipline, the easy concurrent discipline, then you're doing something more clever. You're doing hard concurrency. And then you have two choices. The reason it's called hard concurrency is that you have two choices. You can do a proof of correctness along the lines that I sketched out earlier, or you can have a bug. And there's no third alternative. So the best thing is to stay away from hard concurrency. Okay, that was divide and conquer, by far the most important way of going about implementing your system. The next most important way is to do things incrementally. And there's a variety of aspects of this, but I've highlighted three of them. One of them is indirection, and of course that's especially important today, because one of the things that David Wheeler is famous for is having said that any problem in computer science can be solved with another level of indirection. So there's many different, the basic idea of indirection is somehow you control the name to value mapping. So you can sandwich something in there that you have control over. So virtualization does this. Virtual machines, network address translation, the USB bus, which, if you've ever wondered how your keyboard works when it's plugged in over USB to your computer, as it typically is today, the answer is it works exactly the way the crummy old IBM PS2 keyboard used to work 25 years ago, and that is actually encapsulated in another protocol that virtualizes it, that transfers the bits over the USB bus. But everything is actually being done exactly the way it was being done 25 years ago. So that's another form of indirection. Application compatibility, different versions of the formats that are used for representing databases or documents or spreadsheets or whatever. These are all examples of virtualization, or sort of the poor man's version of virtualization is called shimming, where you have some code and you have some code and you have a client, and they're almost in agreement but not quite, and you put a narrow little thing in between them called a shim that makes them match up. In the network, sort of the bedrock of networking is source routing, where the source of the message says send it here and then here and then here and then here and then to its destination. But if you want the network to have more control over what's going on, you can have IP routing, or you can do things with DNS names rather than addresses at all, or you can have a service rather than a DNS name, or you can give a query and live wild and free. And all those are more levels of indirection piled on top of each other, and many other examples of these things. The other thing that's not quite as good as indirection, but almost as good, is iteration. So you should iterate your designs, you should iterate the actions, you should iterate your components. We talked about redo logging. That's the way redo logging works is you try something and involves several steps. You take step 1, you take step 2, you take step 3, the system crashes. You go back and you take step 1 and 2 and 3 and 4 and 5 and it crashes. You go back and you take steps 1 and 2 and 3 up to 27 and then you're done. And the whole thing is set up. It's not obvious that that will work, so you have to organize the world so that it's okay to iterate like that. And that's sort of the secret sauce of redo logging, but that's the fundamental technique for recovering from failures in persistent systems that have persistent state. Iterating the design, I like to say about user interface design. User interface design is really hard. And the formula that sums that up is the bad UI designer will get it wrong 98% of the time. The best UI designer will still get it wrong half the time. And so there's no alternative to trying it out and iterating the design. Because we're just not smart enough to understand all the implications of things beforehand. And the third aspect of doing things incrementally is extension. And all successful large platforms that have large-scale uptake are designed to be extensible so that you can add pieces to them in a reasonably clean way that won't disturb too much the existing functioning of the thing. So I'll just take the Ethernet as an example. The Ethernet has been through 5 generations. We had 10 megabit Ethernet, and then we had 100 megabit Ethernet, and 1 gigabit, 10 gigabit, 40 gigabit, and we're now just deploying 100 gigabit. That's 6 generations. A number of things have changed. A bunch of stuff has been added. The original packet format is still there, and somewhere in a tiny corner of the 1 gigabit Ethernet chip that's in your PC today is something that understands exactly how to do the original 10 megabit protocol. Even though it's not exercised very often, it's still there. So everything has been done by extension, not by replacement. And that's typically the way we have to evolve successful systems, because replacement is just too hard. But thanks to Moore's law, extension is relatively easy if you thought things through beforehand. Okay, so we did divide and conquer, we did incremental. Now the third major heading for methods is approximate. The basic idea behind doing things approximately is that good enough is good enough. Okay, the reason the web is so successful is that it doesn't have to work. Why does it not have to work? Because it's a person at the other end. And if it doesn't work, you're going to retry it. And if that doesn't work, you're going to try something closely related. And if that doesn't work, you're going to say the hell with it and go and do something else. The software that we were writing 30 years ago did not have these luxuries. So doing things approximately is really great. And there are many aspects of that I'm not going to go into. One aspect that I do want to just touch on is the idea of loose coupling. You should think of the components of your system as being both springy and flaky. So springy means that they're not too sensitive to the details of how they're being connected up to other things. They can adjust themselves to some extent. And flaky means that they might break. I was startled to learn from 2 senior Amazon engineers about 5 years ago the process that Amazon, at least then, used to develop the software for their retail website. This is where you go to buy books, not Amazon Web Services. There are hundreds of modules in this software. Each one is accessible to all the others over their internal network. Each module is developed by an independent team of size approximately 10. They have complete control of the module. They can change it anytime they want. They take the bug reports. And any module is free to call any other module. There's no notion of integration testing or release control or anything like that. So these 2 Amazon guys were explaining this to the Microsoft audience, and the Microsoft audience is starting to foam at the mouth. And their general reason for foaming is they say, this can't possibly work. And that's absolutely true. If you're a customer of Amazon, you may have noticed that not that infrequently, so some of the information that you're accustomed to seeing on some of the pages that it shows you is missing or wrong. It's okay. It doesn't really matter. Agility is much more important. The only page that has to be right is the one that has the orange place your order button on it. And they take huge advantage of that. Okay, so much for methods. Now what about goals? So goals are steady, simple, timely, efficient, adaptable, dependable, and yummy. And we'll just touch on each one of those quite briefly. Why is it simple? Why should it be a goal that your system should be simple? I think it was Dijkstra that said this a long time ago. Simple is important because we can't do much. We're just not that smart. Our brains are not that big. We can build enormously complex things in the computer, and we won't be able to understand them. So we have to work really hard to make it as simple as possible. Is it simple enough? How can you figure that out? Well, you can ask, can I still understand it? But actually, you should be asking a deeper question, which is, what's going to happen when it evolves? Am I still going to be able to understand it? Well, if you haven't used abstraction and interfaces, almost certainly the answer is no. So that's why you should use abstraction and interfaces. It's the only way to keep the complexity under control. And it's well established in the computing world that people way, way, way overestimate their ability to handle complexity. Complexity is cool. It gives you a feeling of power. You feel really good when you've conquered some little bit of complexity. But these are all really bad symptoms, because what's going to happen next is you're going to drown. So resist those temptations. Don't do those things. The other reason why people don't make things simple is that it's actually hard. Simplicity, it's hard to figure out how to make it simple. And often it's not rewarded. You figure out with months of effort how to make something simple. You explain it to your colleague and he says, that's obvious. Well, I can assure you it wouldn't have been obvious to him if you'd just given him the problem and not the solution. So my canonical slogan here is, why did computer scientists not invent the web? And I think the answer is crystal clear. It's because it's too simple. If you had written a paper describing the web and submitted it to SOSP, it would have been rejected on the grounds that this is absurd. Make a new TCP connection for each click on a link? Come on, that's just ridiculous. I went to a morning workshop a couple years ago that was chaired by Tim Berners-Lee, in which the theme was things that should have been done differently when the web was originally designed. And about a dozen things were proposed, 2 or 3 of them by Tim himself. And I sat there listening quietly, and I came to the conclusion that in every single one of those 12 cases, Tim had made the right decision by not doing it. Because every single one of those things would have reduced the ability of the web to be widely deployed far more than it would have increased its value. But this is very countercultural for computer science. So that's simple. Timely. Timely is closely related to approximate. The essential notion is that good enough is good enough. And I said the web is successful because it doesn't have to work. And Microsoft is notorious, not quite so much now as it used to be, but has certainly historically been notorious for shipping fairly poor version 1s of products. And when I joined Microsoft, I used to be extremely negative about this. And I'm not nearly as negative about it as I used to be, because I've learned that from many, many examples, you try to figure out what the product should do, but very often you get it wrong. And you get it wrong in ways that you cannot find out by doing so-called usability testing, where you bring in people off the street for 3 hours to try it out. You only find out by actually shipping it and observing how it gets used. And from that point of view, there's a huge benefit to shipping early and finding out what your users actually care about, as opposed to what you think they ought to care about or what they tell you they care about, which are typically very different things. After all, the users are paid for doing their jobs, not for being able to explain them. Okay, that was simple and timely. Now we have efficient and adaptable. So the most important things about efficiency are, first of all, you need to understand that it's always a balancing act. there are things that are efficient from the point of view of the implementer, what's going to make the code small or run fast or whatever. And there are things that are efficient from the point of view of the client. They're not totally unrelated, of course, because the client would like the thing to be small and run fast. But very often, what's much more important for the client is they can actually understand what it does. Whereas the implementer's interest is in how hard he has to work in order to achieve what he's promised to the client. Adaptable. This is something that was not so important 30 years ago, but it's tremendously important today. You have to plan for success. Successful systems live for a long time. Today's 2015 PC is about 100,000 times better than the Xerox Alto in every dimension. Cycles, RAM, disk, networking. It does maybe 50 or 100 times as much, which leaves the very interesting question of what happened to a factor of 1 to 2,000. And we don't know what happened to that factor. We have some ideas, but no one has ever studied it systematically. But the point is, basically it does the same thing that the Alto was doing in 1976. There are some refinements. We didn't have the web in 1976, and we didn't really have databases, certainly not on the Alto, but just about everything else we had. And so these things evolve over long periods of time. The web itself grew from having 100 users initially to the 10 to the 9th users that it has today. So you have to think about what's going to happen to your system as it evolves, as it adds more features, more components, more users, and so forth. And the other aspect of adaptability is incremental update, because big things necessarily change only a little bit at a time. And finally, you'd like your system to be dependable. So the slogans for dependability are reliable, available, and secure. Reliable means, this isn't quite right what I've written down here, but it's close. Reliable means the system gives the right answers. Available means it gives the answer promptly. And secure means that it works in spite of the fact that bad guys are trying to stop it from being reliable and available. Dependability is, in my view, one of the most difficult goals to deal with, because it's very difficult to figure out how dependable your system needs to be. The American phone system used to have a reputation for being enormously dependable, and the stated reliability goal for an AT&T central office switch was that it should only be down 20 minutes every 40 years, or maybe it was 40 minutes every 20 years, but it's a ridiculous number. To some extent, they cheated by modifying the definition of what it means to be down. But the real point I'm trying to make is not that. It's that there was actually no market demand for this much dependability, which is crystal clear from the fact that today the phone system is much less dependable. You don't hear a lot of bitching. Why was the AT&T system so dependable? Well, it turns out it had nothing to do with the needs of the users. It had to do with the way the regulatory system worked. The regulators would allow AT&T to earn a certain percentage in profit on their capital investment. So more capital investment is better, okay? So it makes sense for AT&T to invest as much as possible in the plan to make it more dependable, until it gets so crazy that the regulators say you can't be serious. And that apparently was at the 40 minutes every 20 years level. So, and finally, this is not something that we can study very well in computer science departments, but in many cases it's really important for your system to be yummy, because if it is not yummy, no matter how wonderful it is, people just won't pay attention to it. Okay, finally, just a few words about performance, because that's something that people often worry about a lot. Michael Jackson has an excellent two-part recommendation about optimizing your code. The first recommendation is don't do it. The second recommendation is don't do it yet. But in spite of that, if you decide that you do need to make your program run faster, the first thing you have to do is measure and find out where the time is actually going. Because usually your intuitions about that are wrong. Well, maybe not usually, but very often your intuitions about that are wrong. The second thing you do is you do a back-of-the-envelope model of your system. and try to get the results that the back of the envelope model gives to be reasonably close to what you actually observe. And typically these models don't have to be very complicated in order to get that close, because usually there's some bottleneck that is determining the performance of the system. After that, broadly speaking, there's a few techniques you can use. You can cache things. RAM caches, file system and database buffers, dynamic programming, lots of different ways to save things. Make them closer to where they're going to be used, at least some of them. You can batch things. So the overhead of getting something going is spread across a lot of the many elements that are in the batch rather than being incurred again for each element of the batch. You can pre-compute. Web search engines like Google and Bing invest a huge amount of effort in both in crawling the web and in building rather complex structures that are optimized for answering queries very quickly. Databases have indexes for the same reason. You can reorder things. So you can do things lazy or speculative. Essentially, you're betting on the future. Doing things lazily is a bet that either you'll have some idle time later to catch up, or maybe that work is not really going to be needed at all. And if we are lazy about doing it, we won't have to do it. Sometimes the right thing to do is to find a better algorithm. If you want to do, this is old news now, of course, but if you want to do fast Fourier transforms, well, it goes like n log n if you use the FFT algorithm, which is now 40 years old. Fairly old news, but not nearly as old as the FFT, is that many problems can be reduced to SAT solving. And SAT solving is with contemporary algorithms, it's still NP complete, but in practice, with contemporary algorithms, I think it's about 1 million times faster than it was 15 years ago. So to sum all this up, I told you about hints and principles. I told you how to think about goals and methods using these slogans of steady by aid. And I told you a lot of things. If you only remember 3 of them, I recommend remembering these 3. Number 1, keep it simple. Number 2, have interfaces to abstractions in your system in order to bound the complexity of what you have to think about at any given time. And number 3, write a spec. You may not do any correctness proofs, but at least write a spec. It'll pay off many times over. And one final hint, not very helpful, but perhaps good to put things in perspective. There's no substitute for getting it right. And on that note, I'll stop and I'd be happy to answer questions.
Great, Butler. Thank you very much. There are 2 microphones just so we can all hear each other. Oliver, off you go. Oh, you're the mic person rather than asking the question person. I thought you were about to ask a question. Anyway, questions, hands up.
Oh, come on.
They're being shy.
These controversial things.
No, they're going to warm up, trust me.
So what do you think about computer scientists putting things out there like self-driving cars? Do you think it could have a major impact literally on society?
Oh, yeah.
Do you think we can get it right?
Do I think that what?
Do you think we can get it right? Or at least right enough?
Oh, yes, because the competition's not that good. I mean, it's down somewhat over the last 40 or 50 years, but still I think every year in the US, 35,000 people are killed in automobile accidents. I have a galactic story about computing, which I will share with you in response to this question. We started out using computers to do simulation around 1950, and whether you simulated nuclear weapons or payrolls, the basic idea was the same. You build some sort of model of the world in the computer, and you run the model and it tells you something about the world. And that was enormously successful, and it paid all the bills for the first 30 years. And it's still paying a lot of bills, and it's by no means played out. Around about 1980, hardware got cheap enough that we could afford to use it for communication between people. And that has brought us email and Twitter and the web and all kinds of great things. And that's been paid even more bills than it did. And it's certainly not played out either. It's got, there are many ways in which we could do the communication much better than we do. But it's been another 30 years. It's time for a new thing. And the NSF, and I call this new thing engagement, and the NSF calls it by the ugly name cyber-physical systems. But what it means is non-trivial interactions between computers and the physical world. And whether that is robots or sensor networks or natural user interfaces or any one of a wide variety of other things, I am absolutely convinced this is going to be the next big thing. Now, today's fad version of it is the so-called Internet of Things. I am fairly confident that the current Internet of Things is going to crash and burn, basically because the value that it affords is not that big, which means that the engineering has to be extremely good, or the thing is going to be a hassle, and it's going to end up in a drawer. And this, for example, and Andy won't like it when I say this, but this happened to Andy's active badges 15 or 20 years ago. I was associated with several labs where they were installed and used for a few months, but I believe that the only lab where they continued to be used was Andy's own lab. And the reason was that they had value, but the hassle was greater than the value that the customer perceived it. And so they didn't stick. I'm sure the Internet of Things idea is going to work eventually. I don't think it's going to work in the current way, because the engineering is just not good. I think there's a good chance, now to come back to your question, that the first big successive engagement will in fact be self-driving cars. And the reason for that is that lots of lives can be saved, and the potential economic impacts are just gigantic in terms of how we can use the roads much more efficiently, and we can use the cars themselves much more efficiently. And people can waste a lot less time than they do now. It's going to be enormously important. People who don't believe in this say it can never happen because of terrible concerns about liability. And I say safety trumps liability every time. If anyone had told you 30 years ago that the car that you buy today is going to have 10 small bombs in it, you would have been laughed at all day long. But in fact, it does. They're called airbags. Other questions? This is very disappointing.
They're just waking up. Quentin, go ahead.
What's wrong here, Andy?
No, they're just nothing. They're waking up.
I grew up with this idea that primitive optimization is the root of all evil. But not sure what Mike is doing.
It's your personality that's doing it.
Too many gadgets in here. But I remember hearing a talk by some of the Google guys about how vitally important they had found every millisecond to be right from the
get-go. There are times when optimization is great. Absolutely. That's why you need all these hints.
Right. So I was going to ask how you decide when optimization is worth it right from the start, if there are sort of general rules, or if
well,
it's a very vague question deliberately.
Most programs that people write are not going to stress the computers on which they run today. This was much less true 30 years ago. But today, you can do an awful lot of things on your 1 billion instructions per second computer without having to worry too much about the efficiency. So you can afford to program in Python and do all kinds of other reckless things. This is a design issue. You have to decide how important the efficiency is compared to the prices that you're going to pay for getting it. You're going to have less agility and very, very likely less dependability for the same amount of effort put in. And the question is, how important is it? Dependability is not tremendously important to Google. They have learned that the latency is very important. And this is a domain in which, although they put a lot of effort into making this response to search queries efficient, there's a huge multiplier because they have so many users. And also, by the way, they have a good way of measuring it because they can actually, to some extent anyway, measure the relationship between latency and clicks on ads, which is what pays the bills. And that's what motivates them to push on this so hard. So that's another big advantage, that you can actually measure the benefits of efficiency improvements rather than just speculating about them.
Alistair.
So you talked about how good it is to have extendability. So Ethernet had a 10 megabit chip in the corner of its gigabit variant. Doesn't this cause trouble in the security domain where we really want to get rid of older versions of protocols and so on?
Well, that depends on your point of view. The canonical rule for dealing with these problems is end-to-end. The reason we have these terrible problems with multiple versions of SSL is that they forgot that. So SSL has a fairly elaborate multi-stage process by which it works out what keys should be used and what versions of all the protocols should be used. And they forgot that if you're going to do things end-to-end, after you think you figured all that out, somebody should say, okay, this is what we decided. Do you agree? They thought that they could do optimization and avoid that. And that opened the door to a lot of bugs. There's no inherent reason why having all those versions is going to be bad. If you make a very complicated, difficult to reason about scheme for adapting to the multiple versions, then you open yourself up to trouble, for sure. This is never a problem in the Ethernet. The fact that there's 6 different flavors of Ethernet is not a security problem.
Ross.
The fact that there's 6 different flavors of SSL definitely is a security problem, but that's because they butchered the design.
Well, we're talking about the Internet of Things, and my observation is that software written by companies whose core competence isn't software is usually dreadful.
Yes.
The software in your cooker, the software in your car, the software in your internet router, all sorts of stuff is beyond horrible. The law tells me that I must use hands-free mobile phones, but trying to dial a phone number from the dashboard of my car is 10 times more dangerous than picking up my mobile phone and just asking it to phone.
So the problem is with the lawyers, not with the software writers.
My question is this: how does this get fixed? You end up having software companies like Microsoft, Google, and Apple taking over the platforms and all the devices in the world, or is there another way to teach other companies to actually write software?
I don't know. I agree with you completely. This is a huge challenge. This is why, for example, the most unreliable part of Microsoft Windows is the device drivers. It's because they're written by people in hardware companies, and there's no career path for programmers. So only in a disk company. So only a bozo is going to go to work as a programmer in a disk company. It just doesn't make sense. This is why the Windows Phone was terrible for so long. Turned out there was we had no business model, and we had some other difficulties about the way we relate to the carriers. And the result of that was that it was a very unattractive place for a good Microsoft programmer to work, and nobody worked there. So they had the C team working on it, and guess what? They produced a C result. And that was subsequently fixed because the priorities were changed. But this is a huge problem. There are some examples that I think suggest that it can be brought under control. I think, for example, the people who build medical imaging systems, they know that software is really important. And they seem to do a fairly decent job. Unfortunately, it's not that easy for the medical imaging system to kill people, so that's a plus too. But no, I don't know the answer. Perhaps over time, more companies will figure out that this is a critical thing and that they have to provide a good career paths for programmers and whatever. Or maybe they'll end up contracting it out. I don't know. It's baffling. But it's always a good thing to think about if you're trying to figure out whether a particular system is going to be any good or not. If there's no career path for the programmer, then the system's probably not going to be very good.
Okay, any more comments for Butler? Great. So
I didn't do a sufficiently good job.
No, you did a brilliant job. So let me say a very, very warm thank you on behalf of the department, on behalf of us all, in making your contribution to the Wheeler Lecture series. which is very special to us. And if I may present you with a just tiny little thing, which we'll post to you if you prefer, but is a little certificate to remind you of this very special day. Thank you very much.
Thank you.